Hey everyone, in this video I'm going to show you a circuit that you can use to interface this force sensor with a microcontroller or some other analog input device. So this is a Flexi-Force A401 force sensor, and it's a sort of like a variable resistor. So let me zoom in and show you how to make this circuit. Okay, so this force sensor is built by laminating two pieces of plastic with some conductive ink on the inside. So the ink is facing, the two inked surfaces are facing each other. So when you apply force this way on the sensor, the two conductive inks are pressed together and the resistance goes down. So if we wanted to interface this with a microcontroller, ATmega or an Arduino or any other sort of analog capture device, we need to figure out how to get this signal into the analog digital converters. So you might be thinking, well, if it's a variable resistance, we can just draw that as a resistance that's variable. And to measure this variable resistance, what we could do is just add another fixed resistor to ground and put this up to some plus voltage source and then take our output here. So we have a voltage divider. But there's a problem. This sensor actually has a curve that looks like this. So if this is force and this is resistance, the graph actually looks like this. So if we were to make a voltage divider like this, it would work. We could measure the voltage using a simple divider like this. But in our software, or in the firmware, we'd have to compensate for this weird-looking curve. So if we actually wanted to make real meaningful force values, force measurements with this sensor, we'd have to compensate for this strange-looking curve. However, lucky for us, there's a way to get around this. So the manufacturer of the sensor has given us this helpful chart showing us that here's the resistance curve, and if we happen to take 1 over the resistance, what we get is this line, which is nice and linear. So 1 over R is the conductance of the sensor, and the conductance is actually very linearly related to the applied force. So as we add more and more force, the conductance goes up linearly. So the trick is, how do we make a circuit that will actually measure the conductance of that force sensor? That way we can just sample the output voltage or sample the conductance and have a linear representation of how much force is being applied. So again, lucky for us, the manufacturer has given us this little chart here, or this little diagram. And this is a very simple opamp circuit. If you're familiar with op-amps, this is an inverting amplifier. And what they've done is put the variable resistance of the force sensor between the inverting input and a negative voltage source. Now in this example they show the feedback resistor being variable, but it could be fixed. And they even helpfully say the feedback resistor should be about 1K to 100K. And the reason for that is when the force sensor is getting near its limit in terms of how much force you can apply, the resistance across the sensor will be, in the range of 10 to 20 kiloohms. So you want to get this value fairly close to this value when it's at its maximum. And the reason for that is this formula here. So if the output voltage is equal to negative VT, which is this negative voltage that we're applying, times our feedback over our series. So if the feedback resistor and the series resistor are about the same value, then we're just going to get this negative voltage times -1, so a positive voltage coming out here. So let me hook the sensor up to the meter and show you this. Okay, so when no load is applied to the sensor, it's essentially open, more than 40 megohms on this meter. And if we apply some force to the sensor, the resistance comes down, so we've got about 800K there. And if I push really hard, the resistance goes down further. Now we've got about 80K. And if I use a bigger area, the resistance also goes down. So for the same force but spread over a bigger area, there will also be a lower resistance. So if I use my thumb to push this down, and I'm pushing pretty hard, I'd say I've got maybe 20 pounds of force on there, it's down to maybe 50K. And if I push really hard, 30K. So it's tough to get it below 30K, let's say, with finger pressure. So one way to build this circuit would be to desire like a 0 to 5 volt analog output. So if we were using an AVR chip with a 5 volt supply rail, its analog digital converter would be comfortable with input voltages between 0 and 5 volts. So let's just say we want an output range of 0 to 5. And we know that the sensor gets down to maybe 30 k ohms when it's fully depressed, when it's experiencing the maximum load for our application. And also, let's just say that our negative supply voltage here is negative 5. So if we write out this equation, we've got, let's go for the high case. So let's say at maximum, we've got 5 volts out is equal to negative times negative 5 volts in times our feedback over the sensor resistance. And we just said that's about 30 k for maximum load. So if we look at this, obviously our feedback is also going to be 30 k, so we can cancel the 5s out, and there you go. So to give this a little bit more headroom, I'm going to choose a slightly lower value. So what would happen if this were exactly 30 k and you pushed harder on the sensor, there would be no additional output swing. So you would sort of top out, and we don't want to run out of measurement room. So by choosing a lower feedback resistor, the sensor will be sure not to run out of measurement room here. So I'm going to pick a value of 22 k for the feedback resistor, 22 k ohm. The next question is, where do we get negative 5 volts? If we're building this circuit and it's going to be powered by USB or powered by a standard wall wart type thing, where do we get the negative 5 volts? One option is to use a part like this. This is a self-contained DC to DC converter, and it is part number SRS0505. It's made by Meanwell, and I got this from Jameco, which is convenient because I live near Jameco and I can just buy this quickly. But of course Newark or Mauser, any of these other guys have it too. And inside here, this is basically a 5 volt to 5 volt converter, but the nice thing is that the output is isolated. So if you put 5 volts in, you can connect the positive output to the negative input and then get negative 5 volts out. So in my circuit, I use this to supply the negative 5 volts that we need to put in over here. Okay, so now we know the feedback resistance that we want. We know how to get the negative 5 volts, and we've got the basic overall circuit layout from the manufacturer. And they recommended that we use an MCP 6004 op-amp, which might be fine. I've never used one of those before. I don't know what the details are. I actually happen to like LM324s. And I read somewhere on the forums that someone said this is like the worst op-amp that's still in production today or whatever. I don't know if that's true or not, but I'll tell you why I like using this chip for this application. I'm going to be measuring forces that are essentially not changing. I mean, AC is not really a concern in this circuit. I basically just want to measure a constant force value, and any rapidly changing forces are not going to be an issue. So this op-amp I don't think has very great AC characteristics, but as far as DC voltages, it's fine. And there's a couple other nice things about it. One is that the output can go all the way to 0 volts. So if we're supplying the op-amp with V plus and 0, the outputs will actually get all the way down to 0, which is very handy. If you've started to work with op-amps, you might have realized that a lot of them require very high voltages on the supply rails, both positive and negative. And so having an op-amp that's able to go down to ground is helpful. Now the outputs won't go up to the V plus. I think they spec it at 1.5 volts under, yeah. So the output swing is 0 volts to V plus minus 1.5 volts. So if we're supplying the op-amp with 5 volts, the output will never be higher than 3.5, which is a problem because we'd be losing signal. This thing would never supply a full 5 volt signal to our ADC, to our AT mega or whatever we're feeding. So one solution is to have a few different voltage regulators in your circuit, and you can feed this chip 6 volts and the rest of the circuit 5, 5 for the AVR. And that way you can get up to 4.5 volts out on this, or use an 8-volt regulator, or whatever you want, just so it's able to have a 5-volt output swing. Another benefit of this op-amp is that it's a quad, and it's available in all kinds of different packages. You can still get this easily in DIP packages, and I like through-hole parts, so that's nice. And it's reasonably okay. I don't think it's that bad of an op-amp, but everyone has their own opinions. You can put that in the comments. Now there's one more addition to this circuit. Since I said that I'm mostly interested in just measuring steady state force values, I'm not really interested in high frequency anything, we're going to add some low pass filters to this circuit. And the easiest way to do that is to put a capacitor here. Now what this does is it creates a single pole low pass filter. Again, not the greatest performing thing, but in this case we can really wipe out, lots of stuff. So I'm going to, well, let's figure out the value. So let's say we wanted to wipe out most of the AC. We'd particularly want to wipe out 60 Hertz because this system is going to pick up 60 Hertz noise from all the wiring. This is actually going to have fairly long wires on it. And the frequency that this is going to start cutting is given by the formula 1 over 2 pi RC. So R is here, C is here, and this formula will give us the cut frequency in Hertz. So the cut frequency looks kind of like this. If we had frequency here and gain or amplitude here, and this is a log-log scale, I think the curve would look something like this. And this is going to go down at, I forget, 10 dB per decade or something. I don't know, you can look it up. Single pole filter, but it's going to come on at a specific frequency, and this frequency is the cut frequency given by 1 over 2 pi RC. So if we were really concerned about exactly what frequency we wanted, we could figure out exactly what capacitors should be used there. But in this case, we're kind of limited by what capacitors are available. So I'm just going to say, let's use 1 over 2 pi R, which is 22K, and C is going to be 0.1 microfarads, so 0.1 E negative 6. And this comes out to be 72 Hertz. So it's not quite below 60. So ideally this should actually be a little bit higher. We could have, I don't have anything quite bigger than this that isn't already 1 microfarad. And for reasons that I'll get into later, it shouldn't be an electrolytic. Okay, so I did some testing and it looks like the 60 Hertz noise is not a problem, so I'm going to stick with this and maybe add another capacitor between the inputs on the op-amp if necessary. So if you're new to op-amps, you might be thinking, well, what we could do to add some more filtering is just from the output here, just add a capacitor going right to ground like that. No, you cannot do this. Most op-amps will freak out majorly if you do this, and the reason is that the output here sets up an oscillating circuit with this capacitor. This op-amp does not have zero output impedance like you would expect from the theory. I mean, if you spend a long time looking at op-amp theory, you'd figure, well, sure, this would be okay. But the problem is that there's actually output impedance with any op-amp, with any real op-amp. And if you add a capacitor here, there's a really good chance you're going to set up a resonant circuit. So at the very best, what you could do is add a resistance, and then you basically have another single pole low-pass filter here, just like you have here. So if you add them together, I think then you have a 2-pole filter, and you can have them at the same cut frequency or even different cut frequencies. Then the only problem is your output impedance going this way is going to be affected by how big that resistor is. So in this case, I don't want to do this. I'm just going to take the output straight from the op-amp so that I have a fairly good output impedance and do all the filtering here or even before. Okay, just like on a cooking show, here's one that I've made previously. This actually has 10 channels to it, but it's the same circuit over and over again, just done 10 times. And these long cables are just so that I can have the force sensors relatively far away from this circuit. This is going into a much larger installation, and the force sensors are going to be some distance away from this circuit. So there's our negative 5-volt generator, and you might be thinking, well, this is no good because I think the switching frequency on that's 40 kilohertz or something, and all that noise is going to propagate right into our output signal. But actually, if you don't load this at all heavily, the output noise is very, very low. These things will get noisy if you start loading up the output, but when they're unloaded, it's actually quite clean. So I'm going to feed this whole circuit with an analog or a linear wall wart. I have had problems using switching power supplies with analog circuitry, and I would pretty much universally recommend against that. Those switch mode power converters are great for digital circuits, but are really terrible for anything analog. So in this case, I have unregulated 9 volts coming in from the wall wart, and I've got a 5-volt regulator here, which just gives this power, and I've got an 8-volt regulator here, which gives the op-amps power. So 8 volts going to the op-amps means that the output can swing up to 6.5 volts. So the output will always be between 0 and 6.5 volts. And normally that would not be preferable for interfacing to something like an AVR, because this thing will freak out if you give it more than 5, and you might run into some current dissipation issues. But in this case, this will actually be connected to this, which can handle -10 to +10 on its inputs. I would actually not recommend this for hobby use just because it's kind of overkill. This is going into a much larger installation with many other pieces. But for hobby use, National Instruments makes a USB 6008, which costs $150 and more or less has half the functionality. It's basically half of one of these. Okay, so let's plug it in and try it out. So here's the power supply that I'm going to use. It's just a 9-volt unregulated 500 milliamp supply. Okay, plug that in. And that's a 2.1 millimeter barrel connector. Plug that one in. And I've got the output from this circuit wired to the scope. And here's the force sensor plugged into my 3 miles of wire there. So when I press on the force sensor, you can see the output on the scope. So the scope is in free run mode, and if I push on the sensor, you can see what the waveform looks like, the force waveform. And if I tap on the sensor like this, you can see the step response there. So what we could do is measure that waveform and see how the step response is not quite ideal. Some of that smoothing is happening because my finger is soft, and when I step on this thing, the force is not increasing instantly fast. But there's also some smoothing that's happening because of the filter that we implemented. So step responses on the force sensor will not be perfectly square because that low-pass filter is going to start smoothing things down. So if I just press on this and hold it steady, you can see there, I think I have it set for a volt per division on the oscilloscope. You can see the response is pretty good, it's working normally. So one other test to make is to switch this to AC coupling, and I'm going to press the auto setup button just to see what we can see. So there is some noise on the output. What's happened here is I've switched to AC coupling, and it's the scope automatically chose 5 millivolts per division, which is as low as this thing can go. And we've got maybe, 5, 10, so 20 millivolts peak noise on there, which is, not great, but not bad either. I've noticed in a lot of circuits, just adding the oscilloscope to the circuit introduces quite a bit of measurement noise. However, this spiking here is most likely from the 5-volt converter. If we had a true linear supply, you could probably get some of that noise down. Here's the signal at 20 millivolts per division. And if I tap on the sensor, you can see how big the signal is compared. I'm just pushing on the sensor very lightly. You can see how big the signal is compared to the noise. So the signal to noise ratio on this system is quite high. I could do a measurement, but just looking at it graphically is usually the best way. You can tell that it's quite good. Okay, well, I hope that was helpful. I'm definitely not an op-amp expert, but if this was at all useful to you guys, maybe I'll do another one on op-amps that are actually working in AC circuits instead of just more or less a DC conversion. Okay, see you next time. Bye.